Have you ever wondered who makes your smartphone, laptop, or even your toaster work? The answer is electrical engineers. They're the brilliant minds that design, develop, test, and supervise the manufacturing of electrical equipment. But it's not just about gadgets. Electrical engineering is a broad field that touches every corner of our lives, from powering our homes to enabling our communications, from running our cars to controlling our industries. Think about it. The alarm clock that wakes you up, the coffee maker that brews your morning cup, the traffic lights that guide your commute, the smartphone that keeps you connected, the air conditioner that cools your summer day. All of these are the fruits of electrical engineering. It's an exciting world of circuits, signals, power systems, and digital design. And it's ever evolving, with new challenges and discoveries at every turn. So, in essence, electrical engineers are the wizards behind the technology we use every day. So, what does the journey of becoming an electrical engineer look like? Well, it all starts with a curriculum that is designed to equip you with the fundamental knowledge and skills necessary to thrive in this field. The curriculum generally includes a mix of general education courses, core engineering courses, and specialized electrical engineering courses. At the heart of it all are the foundational courses, mathematics and physics. These subjects form the bedrock of electrical engineering, providing the tools and principles you'll use throughout your studies and career. Next, we have computer programming. You see, in today's digital age, electrical engineers need a strong grasp of programming languages to design and control complex electronic systems. And then there are the specific electrical engineering courses. These delve into areas like circuit analysis, signals and systems, electronics and power systems, among others. All these courses together help you build a strong understanding of the principles and applications of electrical engineering. The curriculum provides a foundation for understanding the principles and applications of electrical engineering. But what are the building blocks of electrical engineering? The answer is circuits. Now, circuit analysis is all about understanding the flow of electric energy through these circuits. It's like unraveling the secrets of a city by studying its roads and traffic patterns. Imagine a circuit as a bustling city. The voltage is akin to the driving force that pushes the traffic along. It's the electric potential that causes current to flow. The current, in this city analogy, represents the traffic itself, the flow of electric charge. Lastly, the resistance is like the road conditions that can slow down the traffic. It opposes the flow of current. When we analyze a circuit, we're essentially figuring out how these three elements, voltage, current, and resistance, interact with each other. We use laws such as Ohm's law and Kirchhoff's laws to predict how a circuit will behave under different conditions. Circuit analysis is the heart of electrical engineering, and understanding it is crucial to the design and operation of electronic devices. Every circuit has its heroes, and in the world of electrical engineering, they are capacitors and inductors. These two components are like the heart and lungs of a circuit, pumping and circulating electrical energy. Capacitors, much like a sponge, store and release electrical energy in a circuit. They're the ones responsible for smoothing out the power supply and filtering noise from signals. On the other hand, inductors, they're the traffic cops of a circuit. They resist changes in current, helping to keep things smooth and steady. Specifically, inductors come into play when the circuit involves alternating current or AC, where they limit the change in current over time. Capacitors and inductors are also the key players in resonant circuits, which are vital in radio and television receivers. So next time you're tuning into your favorite station or channel, remember, you're able to do so because of these two unsung heroes. Capacitors and inductors, the unsung heroes of the electrical world, play a vital role in the functioning of circuits. AC or alternating current is another key player in the electrical engineering world. AC circuits are fascinating because the current and voltage can change their direction periodically. This is different from DC or direct current circuits, where current flows in only one direction. Now, why is AC so important? Well, it has some significant advantages over DC. AC can be transmitted over long distances with less power loss, which makes it ideal for power supply systems. Think about the power grid that lights up our homes and cities. It's all AC. Even the power adapter for your laptop converts AC from the wall outlet to DC. But AC circuits aren't just about power supply. They're also used in various applications like radio and television broadcasting, and even in the telecommunications sector. In conclusion, AC circuits are a dominant force in power supply, and understanding them is essential for electrical engineers. Signals, the language of electrical engineering. Imagine signals as the unsung heroes of electrical engineering, working behind the scenes to ensure that information is transferred accurately and efficiently. They're the messages or information that are being sent from one point to another, whether in the form of light, sound, or electrical current. Engineers work with signals on a daily basis, observing, analyzing, and decoding them to ensure they're doing their job correctly. Signals can be either analog or digital, with each having its own advantages and disadvantages. Analog signals are continuous, representing physical measurements, while digital signals are discrete time signals, derived from analog signals. But what's most fascinating about signals is their versatility. They can be anything from a simple voltage level in a circuit to a complex data stream in a communication system. So whether it's your Wi-Fi signal or the signal from a remote control to your television, signals are everywhere. Signals, the language of electrical engineering, are a crucial part of the communication process. Fourier series and Fourier transform sounds complicated? Not really. Let's break it down. The Fourier series is a mathematical tool used to represent periodic signals as an infinite sum of sines and cosines. Imagine having a complex signal and being able to break it down into simpler, more manageable parts. That's the power of Fourier series. On the other hand, the Fourier transform, a close cousin of the Fourier series, is used for non-periodic signals. It transforms a signal from the time domain to the frequency domain. This shift in perspective helps us understand the frequency components of our signal, something that's crucial in signal processing. From radio waves to the human voice, these tools help us dissect and understand signals in electrical engineering. Whether you're designing a radio receiver or analyzing the human voice, you'll need these tools in your arsenal. The Fourier series and Fourier transform are key tools for signal processing in electrical engineering. Communication, the art of transferring information. Now consider the role electrical engineering plays in this process. In our interconnected world, electrical engineering is the unsung hero, ensuring that our messages, calls, and data reach their destination. Let's delve a little deeper. You see, communication systems, whether they're your cell phones, internet, or radio stations, all rely on signals. These signals are representations of the data we wish to communicate. But how do we get these signals from one place to another? That's where electrical engineering comes into play. Electrical engineers design and maintain systems that transmit these signals. They ensure that your voice on a call or the text in an email is converted into an electrical signal, sent through complex networks, and then reconverted back into a form that the recipient can understand. So the next time you send a text or make a call, remember the intricate dance of electrical engineering that facilitates it. Electrical engineering plays a vital role in the communication systems we rely on every day. Electronics, the cornerstone of modern technology. Now, let's delve into the role electrical engineering plays in electronics. Electrical engineering is the driving force behind the design and operation of electronic devices that are integral parts of our daily lives. From the simple light switch to the complex supercomputers, all are brainchildren of electrical engineering. It's the knowledge of electrical engineering that enables us to manipulate the flow of electrons, the tiny charged particles, in a controlled manner to achieve a desired outcome. Consider your smartphone. It's a marvel of modern electronics, and it wouldn't be possible without the principles of electrical engineering. The processor inside your phone, the memory chips, the display, the battery, all of these components and their operation hinge on the principles of electrical engineering. In a nutshell, electrical engineering enables us to design, build, and operate electronic devices that make our lives easier and more connected. Electronics, driven by electrical engineering, are the backbone of the technology we use daily. Digital design, the blueprint of the digital world. This is where the rubber meets the road in electrical engineering. It's in digital design that the theories and principles we've discussed come to life in practical applications, shaping the world around us. Digital design is the process of creating digital circuits. These circuits, made up of interconnected logic gates, perform the computational operations that enable everything from your microwave to your smartphone. They're the fundamental building blocks of all digital devices. In the world of electrical engineering, digital design is a critical skill. It's where creativity meets technical knowledge, as engineers design circuits to perform specific functions. Whether it's designing a new processor for a computer or a sensor for a self-driving car, digital design is at the heart of it. But beyond its practical applications, digital design also helps us understand how our digital world works. It's the language of our modern digital age. Digital design, a key area of electrical engineering, is fundamental to the digital world we live in. Power, the lifeblood of all electrical systems. As electrical engineers, we play a crucial role in generating and distributing this vital resource. Let's take a moment to dive into the world of power systems. The generation of power is an intricate process involving the conversion of energy from one form to another. Be it a hydroelectric dam converting mechanical energy to electrical, or a solar panel converting light energy into electrical energy. Each method has its own unique set of challenges and opportunities. Then comes the distribution of power. This involves transmitting this generated power to our homes, offices, and factories. Power grids are the complex networks that make this possible. They're a marvel of engineering, balancing supply and demand, and ensuring that electricity gets where it's needed, when it's needed. Power systems are not just about generation and distribution, they're also about control, efficiency, and sustainability. Power systems, a cornerstone of electrical engineering, keep our world running. Controls, the invisible hands guiding electrical systems. Imagine a symphony where each instrument plays a crucial role. Now, think of an electrical system as that symphony, and the controls as the conductor, guiding and synchronizing each component to create a harmonious output. Control systems in electrical engineering are the sophisticated algorithms and processes that regulate the operation of electrical systems. They ensure that everything from your home's heating system to the most complex industrial machines runs smoothly and efficiently. Without controls, these systems would be like a rudderless ship, adrift and without direction. Think about an air conditioner adjusting its cooling based on the room temperature, or a traffic light system managing the flow of vehicles at an intersection. These are everyday examples of control systems in action. So, whether it's maintaining the desired temperature in your home, or ensuring a factory production line runs without a hitch, control systems play a pivotal role. Control systems, an essential aspect of electrical engineering, ensure the smooth operation of all electrical systems. So, what is electrical engineering? It's a world of circuits, signals, power, and much more. Let's take a moment to recap what we've discussed. We began this journey by understanding the curriculum of electrical engineering, highlighting the various subjects you would encounter. From the basic principles of circuit analysis to the intricate details of capacitors and inductors, we delved deep into the foundations of this field. We explored the complexities of alternating current circuits and signals, and how Fourier series and Fourier transforms serve as powerful mathematical tools. Then, we navigated through the realms of communication, electronics, digital design, power, and controls. Each of these components, while unique in their own right, come together to form the broad spectrum that is electrical engineering. The importance and breadth of electrical engineering cannot be overstated. It's a diverse field, interwoven into the fabric of our everyday lives, powering the world we live in. Electrical engineering, a diverse and essential field, powers the world we live in